Okay, so now we've gotten to the point where we can design our cables. We know enough about the cable geometry, and we did the analysis to calculate the maximum force in our cable. So now I want to take a brief moment to touch on some mechanics of materials or strength of materials, and then get into an example where we'll actually design or select a number of cables for the bridge that we just did the analysis for. So our cables are made of steel. We call them cables, but oftentimes they're referred to in industry as steel wire rope. So that means that they're made of steel. And so I've drawn a stress-strain relationship typical for steel here, with the elastic region, the strain hardening region, and then eventual failure. And I want to note that we have our yield stress. We don't want our bridge to get into this region over here. We want to keep our bridge in the elastic range. We want, and because of that, we can use these simplified relationships for our design. So consider the case where we have axial tension with both. So this is just our cable cut, and this is our tension force that we've calculated now. We actually know the magnitude of that is on each side. So what did we say the maximum was? Our P now is actually 721.8. So we could fill that in. And we also now know the area of our cable, as well as the modulus elasticity. But what's typically given with steel wire rope is not these properties or even the yield stress. What's given is the ultimate breaking strength. They tell us what that is for the specified cable, because the geometries change, and it's a easy quantity for cable manufacturers to test. So we want to limit our cables to never exceed or never get out of this elastic range. So we want them to be existing in this range down here. We never want to get to that yield point. To do that, we want to make sure that the force that we apply to our cable is less than the ultimate breaking strength of that cable. So we use this relationship. P sub S is less than or equal to P sub U over Fx. So what that means is P sub S is the maximum axial tension in kilonewtons, and P sub U is the ultimate breaking strength, also in kilonewtons. And this term Fs stands for factor of safety. So we really want to make sure that our cables don't fail, because if they fail, the entire bridge will not work anymore. So we want to reduce the ultimate breaking strength. So say we had an ultimate breaking strength of 100. Maybe we want to have a factor of safety of 2 and say that, okay, we're never going to let it get to 100. We're never going to let it get to this yield stress. We're only going to let ourselves get to, maybe a point down here of factor of safety of 2. So we're going to limit the stress that our bridge can see. So that's what a factor of safety is, high level. And the factor of safety that we're going to use for the cables, as specified by the bridge building manual, is 3.0. We can use this relationship to figure out the number of cables we need based upon the strength that the strength that's being pulled on them, as well as the ultimate breaking strength, which we get from our in-country program managers. So let's go. It's easiest to show this through an example. So consider that the available cable in country is 1-inch diameter cable. And that specific type of cable has a breaking strength of 85,400 pounds. So using the results from before, determine the number of cables that are going to be required to resist that force. So let's start putting this word problem in and matching it to our variables. So PSU, which was the ultimate breaking strength, that's equal to 85,400 pounds. All right, and what was our P sub S? P sub S was equal to our maximum from our analysis, right? 721.8. 721.8 kilonewtons. But what do we see here? We have a mismatch in our units. So we need to convert from pounds to kilonewtons or vice versa. Since we're doing our bridge design in the metric system, we're going to go ahead and convert the pounds into kilonewtons. This is something that you'll run into a lot, is a lot of the cable breaking strengths are oftentimes given in imperial units, and you'll need to convert them into SI units. So to do that, we need to first we need to do some dimensional analysis, and we need to go from pounds through kilograms into newtons. So first let's convert from pounds to kilograms. We know that 1 pound is 0.454 kilograms. And then we know that 1 kilogram is equal to 9.81 newtons. And now from newtons to kilonewtons. 1,000 newtons is 1 kilonewton. I'm going through and doing this. I know it's pretty simple, but if you haven't designed in the metric system for a while, this is something that will trip you up, and I want to at least get one example of how to convert between pounds and kilonewtons. Okay, so if we run through all this, we get that P sub U is equal to 380.3 kilonewtons. I'm just going to bring P sub S down here as well, just so we have them next to each other. Okay, so there's P sub U and P sub S. So if we had one cable, it's not going to cut it, right? One cable, so each cable has a strength of 380 kilonewtons. And if we just had one of them, we put 721 on it, we're just going to break that cable real quick. But what we can do now is use this relationship, this relationship here, in order to identify the number of cables we need. So I'm going to modify it a little bit and modify it to be P sub S over the number of cables. So taking the applied load and assuming it gets distributed equally between all of our cables, needs to be less than or equal to P sub U over the factor of safety. So this assumption where it gets divided evenly over all the cables is a simplification. Typically, you'd want to separate it out by stiffness, which we'll get into in the advanced design course. But for now, we're going to use this relationship to calculate the number of cables, but know that there is a more precise way of doing it using the method of stiffness for developing your load path. So I want to make that note. Okay, so now let's plug in all of our numbers here and solve for n. So P sub S was 721.8 divided by n needs to be less than or equal to 380.3 divided by our factor of safety, which is 3.0. And if you solve for n, we get that n needs to be greater than or equal to 5.69, and our units all cancel out here, right? This was kilonewtons, and that's unitless. So our number of cables is also unitless. So it needs to be greater than 5.69. Well, we can only have cables in even numbers, and if this is the only cable that's available to us, that means that n is equal to 6. And we need 6 cables. Let's think about how the geometry of these 6 cables might be achieved. So I'm going to draw a cross-section of a bridge real quick, where we have our 2 handrail cables are up like this, and we know that we need to have 2 walkway cables on either side to support the crossbeams. This is just the minimum configuration of cables that's possible. So right now we have 4 cables, and we need to figure out where we're going to put these other 2. One option would be to put the other cables right next to there, and we could get to our 6 cables. But another option, see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, would be to maybe put the cables in the middle. We put 2 cables in the middle, and we still have a symmetric loadout. And to clarify what I'm saying here, I realize I didn't explain that very well. This is where our cross beams will sit, and then this is where our suspenders, loop around like that, something like that. But now we need to recognize that these cable configurations depend upon the type of crossbeam we're using. In order to have only cables at the edges and to not have a center cable, we need to be using steel crossbeams, because that's one of the requirements of our walkway analysis. If we're using wood crossbeams, we would use this other geometry. So this is something to recognize when you have a large number of cables like this, is to choose the configuration is going to depend on the configuration of the walkway cables will depend upon the type of crossbeam you're using. So 6 cables is a lot. How might we reduce the number of cables we need? Well, what are the variables we have to change? We have N, factor of safety, P sub U, and P sub S. Well, we're trying to reduce N, so that's the one we're trying to change eventually. Can we change our factor of safety? No, that's a requirement of the bridge builder manual and the design of these bridges. It needs to be at least 3. What about P sub S? Can we change the applied load on our bridge? We might be able to change some of the geometry to reduce P sub S. We could move our abutments or something. But that was pretty hard to change. But what about P sub U? P sub U was a given based on the number of cables we had, or the size cable we had. We had 1-inch diameter cables. If we use a larger size cable, we would have more available strength, and this 85,000 pounds might jump up to somewhere around 110,000 pounds for, say, an 1.125" cable, and then even up to over 120 for an 1.25" cable. So if we had higher or larger diameter cables with higher braking strengths, we'd be able to increase our ultimate strength, and that would then decrease the number of cables required. And we might be able to get down to, say, 5, maybe even 4 cables. We can't go lower than 4, though, right? Because we need 1 in each corner for our deck to sit on. All right, so we've gone through and designed the number of cables and the configuration of our bridge based upon our cable analysis. I also want to scroll all the way back up and just revisit our learning objectives for the cable analysis section. So by now, you should be able to differentiate and articulate the 3 different types of sag. So there was hoisting sag, dead load sag, and the third one was live load sag. And you should be able to explain those, and I suggest it to really capture or summarize your understanding of it, sketch it out, and write down the equations. Try to do it from your head, but feel free to look at your notes as well. But go through that exercise. The second thing that you should be able to do is calculate all the forces in the cable. No need to memorize all these equations, but understand where all these calculations come from. Third, you should be able to select the appropriate size and number of cables. We just covered that in this last little bit. And then lastly, this learning objective relates to increasing your engineering judgment and know-how. But I wanted you to be able to compare the tension in the cables and how that changes based upon different geometric variables. So I've talked through a couple examples of that. What I talked about was not exhaustive, though. So if you can start to think about this on your own time of what different elements you can change to make your design more efficient or reduce the forces depending upon your topography, that's sort of the next step, and that will lead to more efficient designs and help you become a better engineer.